This video will introduce the concept of reflectivity and how it's dependent on angles in particular for the intermediate lab. The picture on the right is one of the pictures that we're going to emphasize during this description. The learning outcomes for this lab are to understand the dependence of reflection on incident angle and also to build skills in comparing experimental data with theoretical calculations. So we're going to do our best to actually acquire some experimental data and plot it, compare it with the theoretical calculations that we expect to see. Also, the concepts of reflection, we've got reflection everywhere around us. Light is always reflecting off of things and reaching our eyes. And it gives us a new view when we can think about how that light is changed on reflection. What we're going to study today is under what conditions is there a lot of light reflected and when is there not. Different kinds of materials, different angles, again in particular. And we're also going to see how it affects the light when it's reflected. There are two primary lab objectives. The first is to measure the reflectivity of the prism or glass cube, whatever it is that you're given, as a function of the angle of incidence and the polarization state. So you'll measure this for both parallel and perpendicularly polarized light, and then compare those to reflectivity plots of the Fresnel equations. There are descriptions of how to do that there. And then we're going to look at prism angles, and we're going to look at the light going through a prism and study the angle of deviation for it. So let's start off simple. The law of reflection says that light bounces off of a surface at the same angle at which it hits the surface. And what we say as an equation is theta I equals theta R. The angle theta is defined relative to the normal being perpendicular to our surface. So in this case, the black line is our surface, the dotted line is the normal, and the red line is our incident beam and our reflected beam. And another basic piece of information is that when light travels through a material, it is different than when it travels in a vacuum. When it travels in a vacuum, like space, it travels at the speed of light, c. But in any other material, it slows down. What we say to describe that slowing of light is that the medium has an index of refraction, n. And the index of refraction is actually what defines the speed in a medium, or vice versa. The speed of light in a particular medium is c, the speed of light in a vacuum, divided by the index of refraction of that light. So typical values are things like air, we typically say has a value of index of refraction of 1. And water, we typically say has an index of refraction of 1.3, glass about 1.5. Now let's look at what happens to the electric field at an interface. This is a little bit of basic physics, and the details help us to understand that reflectivity depends on the polarization of the electric field. It will seem a little bit out of context, but we're going to go through it anyway as a reminder of what you've done, or just as a setting for what we're going to do now. So some of the things that you remember from General Physics 2 or from E&M are the Maxwell's equations in particular forms. And this Maxwell's equation tells us that the tangential components of the electric field are continuous. And this tells us that the tangential components of the magnetic field are continuous. So in other words, the tangential or parallel components of an electric and magnetic field are continuous across an interface. And that's what this shows. Like when the electric field bends, the tangential components have to stay the same. So if the incident, reflected, and transmitted rays all satisfy these particular boundary conditions, then that defines their magnitudes. The magnitudes are going to be continuous across the interface, and their phases are also going to be continuous across the interface. We're saying all this to derive for us the law of reflection and of refraction. So this actually tells us this great statement Maxwell's equations tells us this amazing statement, which is Snell's law and the law of reflection. Snell's law is Ni sine theta I equals Nr sine theta R, and the law of reflection is theta I equals theta R. All right, well, now let's jump into, from that little description of physics, let's jump right into how we define planes and angles. We have something called the plane of incidence. And this is the plane in which all the incident, reflected, and transmitted rays lie. So here, the first picture on the right here has an incident ray, which is this red line, reflected ray, which is this one, and a transmitted ray here. All three of these lie in the plane of the screen, and that means that the plane of the screen is the plane of incidence. The dotted line is the normal, and that's how we define the incident angle and the reflected angle and the transmitted angle relative to the normal. And we can now define the electric field as either parallel to the plane of incidence, as it is in this picture, or perpendicular to the plane of incidence. Here, the electric field is now coming out of the page, perpendicular to the plane of incidence. So here we go again. If you were looking down on your laser beams bouncing around on your table, the table plane would be the plane of incidence. And rays that are, when the electric field is polarized parallel to the table, it would be parallel to the plane of incidence. When it's polarized perpendicular to the table, it would be perpendicular to the plane of incidence. So we've talked about this because reflection and transmission is actually different whether your light is polarized parallel or perpendicular to the plane of incidence. And this is determined by the Fresnel equations, which come from Snell's law and Maxwell's equations. So in the case where our electric field is polarized perpendicular to the plane of incidence, we get these lovely expressions between the incident electric field and the reflected electric field, and then also the incident electric field and the transmitted electric field. So this is what we call R perpendicular. That's useful to write down that little R perpendicular expression. And guess what? When we have light polarized parallel to the plane of incidence, we have our R parallel expression. And again, this is useful to write down. So to summarize, the Fresnel coefficients look like this. What we will be talking about today is external incidence, where where Ni, the incident index of refraction, is less than the transmitted index of refraction, for example, air into glass, or air reflecting off of glass. And when we calculate these Fresnel coefficients, they look something like this if we plot them. So the picture on the left is for external incidence. The picture on the right is for internal incidence. We'll be emphasizing the external incidence, which is the picture on the left. The red lines are reflection. So notice that the reflected light is very, very different whether your light is polarized parallel to the plane of incidence or perpendicular. And this is one of the most useful things about polarization, about reflection, which is that we can polarize light by reflecting it. And this comes to Brewster's angle. So in optics and in electricity and magnetism, we can see that dipole radiation doesn't emit along the axis of the radiating dipole. And let's look at this picture on the right here. We've got our incident beam, and our electric field is now polarized parallel to the plane of incidence. That means when it reaches the surface here, it's going to bend a little bit, and the electric field is now going to vibrate like this double arrow. It's going to make material, any atomic dipoles in this glass material, vibrate also in this direction. Well, they can radiate just fine along this transmitted line, but they can't radiate any energy along the direction of reflection. And light has to reflect along that direction. In other words, there is no reflected light that is polarized parallel to the plane of incidence. So at that particular angle, which coincides with the oscillating angle of the dipoles, light is only polarized along the plane that contains the reflecting surface. Okay, that was a bit of a mouthful. So in red here, a little bit easier to understand, light polarized parallel to the plane of incidence, as we've drawn it here, is not reflected, and light polarized perpendicular to the plane of incidence is reflected. For something like glass, this is about 57 degrees or 0.99 radians. Let's turn that into this plot here. That means that one of these reflected rays, one of these reflected coefficients should go to 0. And in fact, it does. Let's look at this line here. It goes to 0 right around 1 radian. Well, that's good because that's what we calculated. And that is the parallel component. The perpendicular component, however, does not go to 0. So right here at this angle, we will not see any parallel component, but only perpendicular. The phase also changes on reflection. We will not get into that this time, but I have given you a little bit of information about phase in your MATLAB plot. Well, okay, so we've been talking about electric fields. And the fact is we don't measure electric fields. We measure power. Power is proportional to the square of the electric fields. So now we define the reflectivity and transmissivity are capital R and capital T. Written those again here. I've given you a set of MATLAB code so that you can plot the reflectivity and transmissivity if you wanted to, but we only really care about the reflectivity of different indices of refraction, incident and transmitted indices of refraction. So here, let's look at, these are the coefficients we were just looking at, and this plot below is the reflectivity and transmissivity. So the main thing to notice is that reflectivity is 0 at an angle 0, and it goes to 1, it goes to 1 as we reach what we call grazing incidence, or an angle of pi over 2. So at pi over 2 or 90 degrees, you expect to get a maximum amount of energy reflected, and at 0, you expect to get very, very little reflected. It's actually not 0, but it's very, very low. So we're going to calculate acquired data for these plots and plot our data on the same axes as the calculated coefficients. The new equipment that you'll have for this lab, in addition to other things that you've used before, are rotation mounts for things like wave plates or polarizers, and a mount that will rotate along the perpendicular axis for something like a glass cube or a prism that we can reflect light off of. Our pre-lab questions are to think about what you're going to do in the lab. So first, sketch the beam path when it reflects off of the off of a glass prism or a glass cube as described in the first objective, and draw what the parallel and perpendicular polarization directions would be. Second, determine how you will decide the polarization of the laser, and how will you change the light in order to measure reflectivity with parallel and perpendicular polarizations. As you get started with your group, just compare your pre-lab activities, which are essentially your hypotheses, and of course sketch your experimental setup and continue on from there.